Cryptography fundamentals. Let me introduce myself. I am VISHNU, Cybersecurity Analyst, BCBUZZ Technology of Coinbase. What we are going to see about today is fundamentals and introduction and why are we using it, what are the histories, evolution and goals of it. Cryptography fundamentals. Cryptography fundamentals are the pillars of modern cybersecurity that enable secure communication in an inside digital world. It is the scientific discipline and that protects information by transforming readable data, known as plain text, into an unreadable form called text using mathematical algorithms and secret keys. The purpose of this is transformation is not just easy, but structured security. Cryptography ensures that digital system remains trustworthy whether in online banking, cloud storage, blockchain transaction, of secure message platforms. In today's interconnected ecosystem, almost every secure digital interaction depends on cryptographic mechanism working slightly in the background. Unstructured and undesigned cryptography means understanding how digital trust is built and maintained. Introduction. Cryptography is both a science and an applied protection focused on protecting information from unauthorized access. At its core, it uses complex mathematical techniques to encode data so that only intended receipts can be interpreted. The readable input or plain text undergoes an encryption process using a specific algorithm and a cryptographic key, producing cryptext that appears random and meaningless to outsiders. Only some processing that appropriate key can reverse this process through decryption and recover the original information. Modern cryptography is designed around four essential security objectives: confidentiality, which restricts access to unauthorized users; integrity, which ensures data remains unaltered; authentication, which verifies identification; and non-repetition, which prevents denial of access. These objectives collectively form the background of the secure digital communication system. Why cryptography is important? Cryptography plays a critical role in protecting digital infrastructure and sensitive information. In the absence of encryption, data transmitted over networks could be easily interrupted, modified, or stolen by attackers. Every secure website connection, online payment transaction, cloud storage service, and secure email communication relies on cryptographic protocols to function safely. From a cybersecurity perspective, cryptography strengthens defensive mechanism by ensuring that even if attackers gain access to interrupt data, they can interrupt it without the correct key. It scientifically reduces risks such as identify theft, financial fraud, and data breaches. Furthermore, in security testing and vulnerability assessment, evaluating the strength of cryptographic implementations is essential because weak encryption can completely undermine an otherwise the secure system. Therefore, cryptography is not optional in modern system; it is foundational. History of it. The history of cryptography spans thousands of years and reflects humanity's constant needs to protect sensitive information in ancient civilizations such as Egypt, Greece, and Rome. Early encryption method involves simple substitution technique where letters were replaced with the other character to obscure meaning. One famous example from classical replaced with other character to obscure history is Gaussian zipper, which shifted letters by fixing number to position. As communication systems evolved, particularly during wartime periods such as World War One and World War Two, cryptography advanced from manual methods to mechanical encryption, machines that increased complexity and security of that time. The development of computers in the 20th century marked a turning point, enabling the creation of mathematically algorithms that could provide stronger and more scalable protection today. In future, cryptography is deeply integrated into digital systems and relies on advanced mathematical principles rather than series of methods, representing a significant evolution from its classical originals. Evolution from classical to modern cryptography. The transformation from classical to modern cryptography reflects technical progress and the increasing complexity of communication network. Classical cryptography technique relied primarily on substitutions and transportation methods, where characters were rearranged or replaced to conceal messages. Although these methods were effective for their time, they were vulnerable to frequency analysis and systematic attacks. The emergence of computers introduced modern cryptography, which is grounded in mathematical hardness. Assumptions such as difficult of factoring large prime numbers or solving discrete algorithms problems. Unlike classical systems, modern cryptographic algorithms are designed to withstand mathematical analysis and large-scale computational attacks. This shift has been enabled secure global communication, digital commerce, and encryption cloud infrastructure. Modern cryptography no longer depends on hiding the algorithm, but instead of depending entirely on the strength and security of the cryptographic keys. Core goals. Cryptography is built around four fundamental security objects that collectively establish trust in digital system. The first objective, confidentiality, ensure that sensitive information is accessible only to authorized individuals. This is achieved through encryption mechanisms that convert plain text into hypertext, making it unreadable to anyone who does not possess the correct decryption key. The second objective, integrity. It grants that the data remains unchanged during storage or transmission. Even a single unauthorized modification must be detected, which is typically achieved using cryptographic hash functions or messages authentication codes. The third objectives, authentication verification. The identify of the user, devices or systems involved in communication. Through digital certificates and cryptographic key validation, system can confirm that the communication party is legitimate. The final objective is non-reputation. It ensures that the sender cannot deny having sent a message or performed a transaction. This is particularly important in legal, financial, and contractual digital environments. Together, these four goals form the structured foundation of all the secure communication system in the cybersecurity. Basic terminology in cryptography. Understanding cryptography requires familiarity with its foundational terminology. Plain text refers to the original readable data before any encryption is applied. Once an encryption algorithm processes the plain text using cryptographic key, it transforms it into ciphertext which appears random and unintelligible to unauthorized observers. Encryption is the process responsible for converting plain text into the Hypertext, which decryption reverses that process to recover the original data using the appropriate key. A key is sequenced of bits that controls how the algorithm perform encryption and decryption. The strength and security of this key largely determine the overall security of the system. This text refers to an actual mathematical algorithm used to perform encryption and decryption operations. Cryptanalysis is the practice of attempting to break cryptographic system or recover keys without the authorization or unauthorized users, often by analyzing patterns or exploitation of the weakness. Cryptography in construct is the broader discipline concerned with designing security systems. These fundamental terms provides the concept of the vocabulary necessary of the understand advanced cryptographic mechanisms. Key in cryptography. A cryptographic key is a critical component that determines how encryption and decryption process function within a secure system. It is essential and sequential of bits or characters that works in the combination with the cryptographic algorithms to transform plain text into ciphertext and vice versa. The strength of the cryptographic system does not depend on hiding the algorithm itself, but rather than the protecting the security and complexity of the key. The principle ensures that even if attackers understand the encryption method, they cannot hide the algorithm itself. Keys can vary in size, and generally longer keys provide stronger restriction against brute force attacks. In symmetric encryption systems, the same key is used for both encryption and decryption data required both parties to securely share the protected key and the data information. In asymmetric encryption systems, two mathematically related keys are used: a public key for encryption and a private key for decryption. Proper key management includes secure generation, storage, rotation, and revocation. It is essential because the compromisation of the key can completely undermine the security of the encrypted data. Symmetric key in cryptography. Symmetric key cryptography is encryption method where a single shared secret key is used for both encryption and decryption. In this approach, the sender and receiver must both possess the same secret key before secure communication can occur. The encryption algorithm takes the plain text and the shared key as an input, producing the new text of that appears random to anyone without the key. Because the same key is used to reverse the process, the receiver applies the identical key to decrypt the text and recover the original message. Symmetric encryption is known as the speed and effectiveness, making it ideal for the encryption. Large amount of data such as files, database, and real-time network communication were used. It is widely implemented in the secure storage system, disk encryption, and VPN communication. However, the major challenges lies in securely distributing and managing the shared keys, especially in large networks where multiple users require security communication channels. In entire environment, full disk encryption solutions use symmetric algorithm to protect sensitive data stored on laptops and servers. For example, Windows BitLocker uses symmetric encryption internally to secure disk data. Even if an attacker steals a laptop without the correct decryption key, the stored files remains unreadable. Similarly, cloud provides encryption stored customer data using symmetric encryption to ensure confidentiality even if stored infrastructure is compromised. You can also relate this to the ransomware. Ransomware attackers themselves use strong symmetric encryption to lock victim files because it is externally fast and effectiveness for the encryption thousands of files quickly. That makes the audience realize symmetric encryption is powerful enough to be used by the both defender and attackers. How it is worked. In symmetric encryption, the process begins when the sender takes readable data, known as plain text. They applies an encryption algorithm along with the secret shared key. The algorithm performs a series of mathematical transformations controlled by the users, converting the plain text into cheaper text. Clipper text. This text is then transmitted across the communication channels, which may be insecure public. Since the data is encrypted, even if an attacker interrupts it, they cannot interrupt it, meaning without the key password. When the recipient receives the text, they apply the same secret key using the corresponding decryption algorithm, which reverses the transformations and restores the original plain text. The security of this method depends entirely on keeping the shared key confidentiality using an sufficiently strong key length to resist brute force attempts. Because symmetric encryption is computationally effective, it is common used for bulk data protection in the modern systems. Advantages of it. It provides several significant benefits that makes it practical choice. Many security applications. One of its primary advantages, highly performed asymmetric algorithms are designed to process data rapidly within minimal computational overhead. This makes them suitable for encryption, large files, streaming data, and full disk. Additionally, symmetric encryption requires less processing power memory compared to asymmetric methods. It allows it to function effectively when on resource-constrained devices such as mobile phones and embedded systems when implemented with the strong key length and modern algorithms. Symmetric encryption offers robust protection against brute force and unauthorized users. Its relatively simple design also make it easier to implement and integrate with secure infrastructure. Due to these strengths, symmetric encryption is often used as the primary method for protecting data once a secure communication channel has been established. Limitation of symmetric encryption. Symmetric encryption has important limitations that must be carefully managed. The most significant challenge is secure key distributions, as both parties must obtain the same secret key without exponentiating it attackers. If the key is encrypted during transmission, the entire communication becomes compromised. In large-scale systems with multiple users, managing shared key becoming inconsistency complex because each pair has an unique and users ideally requires a unique key. As the number of users grows, the number of required key increases rapidly. creating scalability issue. Furthermore, symmetric encryption does not provide non-reputation. Since both parties use the same key, past and future encryption communication protected by the key makes become vulnerable. Therefore, while symmetric encryption is powerful, it is the often combined with the cryptographic techniques to address these weaknesses easily. Asymmetric cryptography. Asymmetric key cryptography, also known as public key cryptography. It is an encryption approach that uses two mathematical related key instead of single shared key. These two keys are used known as public and private key. The public key is openly distributed and can be shared with anyone, while the private key is kept strictly confidentiality by its owner. The unique mathematical relationship between these keys ensures that data encrypted with one key can only be decrypted with the other corresponding key. This mechanism eliminates the need to share a secret key in advance, solving one of the major weaknesses of symmetric encryption. Symmetric cryptography is particularly important in secure internet communication, digital certificates, email encryption, and online transactions. It not only enables confidentiality but also forms the foundation for digital signatures and identity verification in modern cryptographic systems. How it is work. In asymmetric encryption, every user generates a pair of keys consisting of the public key and the private key. The public key is distributed openly. Often, digital certificates are public directories, while the private key remains securely stored with the owner. When a sender wants to transmit confidential information, they encrypt the plaintext using the recipient's public key. Once encrypted, the data becomes hypertext and can be safely transmitted over public and insecure networks. Even if an attacker interacts the text, it cannot be decrypted without the recipient's private key. Upon receiving the text, the recipient applies their private key to decrypt it and recover the original plaintext. Asymmetric cryptography can also be reversed for digital signatures, and the sender encrypts a message hash using their private key. And other than verification, it is the sender's public key. This ensures authentication, integrity, and non-reputation in digital communication. Advantages. One of the most significant advantages of asymmetric cryptography is secure key distributing. Since the public keys can be openly shared with compromising security, there is no need to transmit secret key through insecure channels. This greatly reduces the risk of the interception during key exchange. It is done because the private key is never shared. The export risk is minimized compared to symmetric systems. Asymmetric cryptography also enables digital signature, which provides strong authentication by verification the identification of the user. This capability of ensures that the message originates from legitimate scale and large network because each user only requires one key pair rather than multiple shared keys. Cryptography essential for secure web browsing, ensures email system, software signing, and digital certificate systems. Limitations of asymmetric cryptography. Although asymmetric cryptography provides strong secure benefits, it is also has an Performance limitations: the mathematical operations involved in the public key algorithms are computationally intensive, making them significant slower than the symmetric encryption. As a result, asymmetric methods are not suitable for encryption large volume of data directly. They also require more processing power of memory, which can affect performance in the resource constraints environment. Another limitation is the complexity of implementation and key management, as improper configuration can introduce vulnerabilities. Additionally, asymmetric algorithm requires much larger size key to achieve equations compared to symmetric algorithm, increasing storage and computational requirements. Due to these constraints, asymmetric cryptography is typically used to secure key exchange and digital signature, while symmetric encryption handles bulk data protection. Hybrid cryptography: hybrid cryptography combines the strength of the both symmetric and asymmetric encryption to create a balanced and efficient secure system. In this approach, symmetric cryptography is first used to securely exchange the symmetric session key between communicating parties. Once the session key is securely transmitted, symmetric encryption is used to encrypt the actual data. This method leverages the secured key distribution advantages of asymmetric cryptography and the high speed efficiency of systematic encryption. Hybrid cryptographic systems are widely implemented in secure communication protocols such as SSL or TLS. Hash function is a cryptographic algorithm that takes input data of any size and converts it into the fixed length output known as the hash value or message digest. Unlike encryption, hashing is not designed to be reversed. It is one-way process. This means that when data is transformed into a hash, it is computationally ineffective to retrieve the original input from the hash output. A system characteristic of hash function is that even a minor change in the input, such as modifying a single character, produces a completely different hash values. This behavior is known as the effect and then critical for detecting data tampering. Hash functions are widely used in password storage systems, where the actual password is not stored but instead of it hash is saved. They are also fundamental in ensuring data integrity, verifying software downloads, securing blockchain transactions, and supporting digital signature mechanisms. Because of their one-way nature and integrity verification capabilities, hash functions are the modern cybersecurity architecture. Properties of it: for hash function, it's to be considered secure and reliable in cryptographic systems. It must satisfy several critical properties. First, it must be deterministic, meaning the same input will always produce the same hash output. This consistency is essential for reliable data. Second, the function must produce the fixed length output regardless of the input size, ensuring uniformity in storage and comparison process. It must be executed pre-image resist, meaning that give an hash value. It should be particularly impossible to determine the original input that produces it. Next, it must be provide second pre-image restriction, which ensure that if an attacker is given one input and its hash, they cannot find a different input that generates the same hash. Finally, it must ensure following restriction, meaning it should be ineffective to find two different inputs that produces identical hash function. It's particularly important in digital signature and blockchain systems become cloud undermine trust and data integrity. Together, these properties ensure that secure hash functions can reliably protected against tampering of the forgery attempts. Digital signatures. Digital signatures are cryptographic mechanisms that provide authentication, integrity, and non-reputation in digital communication. The process begins by generating the hash of the original message using a secure hash function. This hash uniquely represents the message content. The sender then encrypts this hash using their private key, creating the digital signature. When the receiver obtains the message and its signature, they decrypt the signature using the sender's public key to retrieve the original hash function values. The receiver then independently generates a new hash of receiving message and compares it within the decrypted hash. If both values match, it confirms that the message has not been altered and that it was indeed sent by the holder of the private key. Digital signature and widely used in secure email system. On banking transactions, software code signing, and legal digital documentations, they establish trust in digital environment by ensuring both authentications and accountability. Digital signatures are heavily used in software development. When a company releases software updates, they digitally sign the update package. Your operating system verifies this digital signature before installing it. If a signature is invalid, installation is blocked because it could indicate tampering. You can also mention e-commerce transaction online banking system use digital signature to validate transaction authenticity, ensuring the transactions are genuine, authorized by account holder. This highlights the authentication and non-reputation. Public key infrastructure. Public key infrastructure, commonly used as PKI, it is a framework that manages digital certificates and public key encryption that enables secure communication over networks. At its core, PKI binds public key to verified identification through digital certificates issued by trusted entities called certificate authentication. When a user visits a secure website, the server presents a digital certificate that proves its identity. The certificate authenticity verifies the authentication of the certificate, ensuring that the public key truly belongs to the claimed organization. This system prevents attackers from legitimate website and protects users from main authentication. The man-in-the-middle attackers (PKA) supports secure web browsing and encryption, email VPN authentication. Cryptographic algorithms. Cryptographic algorithms are structured mathematical procedures designed to secure information by transforming plain text into ciphertext and vice versa. These algorithm forms the technical backbone of modern systems and are categorized based on their operational principle. Symmetric algorithm uses a single shared secret key for both encryption and decryption, making them highly effectiveness and suitable for protecting large volumes of data. Asymmetric algorithms, on the other hand, operate using a pair of mathematical related keys, a public key and a private key, are primarily used for secure key exchange and digital signature. Hashing algorithms differ from both encryption and decryption methods because they generate a fixed length digit code from input data without the intention of reversing it. Each category of algorithm serves a distinct purpose with the cybersecurity framework, and a modern security architecture often combines them to achieve op- optional performance and protections. Cryptographic attacks. Cryptographic attacks are deliberate attempts by the compromission of encryption systems, recovers secret key, digital signatures. One of the simplest forms is the brute force attacks, where an attacker systematically attempts every possible key combinations until the correct one is found. The flexibility of each such an attacker's largely depends on the key length and computational power. A text-only attack occurs when an attacker has access only an encrypted message and attempts to reduce patterns. The plaintext or keys. In a non-plaintext attack, the attacker possesses both plaintext in its corresponding text and uses this information to analyze the encryption mechanisms. Another significant threat is the man-in-the-middle attack, where an attacker secretly encrypts the potential alerts communication between two parties, particularly during key exchange process. These attackers highlight the importance of using strongly algorithms, sufficient key length, secure key exchange protocols, and proper implementation techniques to defend against exploitation. When explaining exploiting brute force attacks, mention password cracking tools used in the penetration testing. Weak encryption keys or short password can be cracked if sufficient computation power is available. For man-in-the-middle attacks, given Wi-Fi example, if someone connects to an malicious public Wi-Fi hotspot, an attackers could be interrupted communication during key exchange if certificate validation is weak. Blockchain cryptographic plays a fundamental role in blockchain by ensuring security, transparency, and immutability. Blockchain system cryptographic hash functions are used to link blocks of transactions together in a sequential chain. Each block consists of hash of the previous block, creating a dependency structure where alerting and data in one block changes its hash and breaks the entire chain. This properly makes the unauthorized modification easily detectable and preserve data integrity. Additionally, asymmetric cryptography is used to manage digital identities. Within blockchain networks, users generate a public key and a private key pairs, where the public key serves as an address of receiving digital assets, and the private key is used to create digital signature authentication transactions. In blockchain systems like cryptocurrency networks, every transaction is signed using the user's private key. If someone gains access to your private network, they can transfer your funds. That is why hardware wallets are recommended for storing cryptographic private key securely. Also mention that because of block references, the previous block's hash alerting post transaction becomes computational and preventing immutability. Cloud security. In cloud security environments, cryptography ensures that the sensitive data remains protected, both at rest and the transit time. Data at rest transfers the information stored in the cloud services, while data is transit refers to information begins transmitted between users and cloud services. Symmetric encryption is commonly used to protect stored data due to its speed and effectiveness. For secure communication channels, asymmetric encryption is used to establish encryption sessions between clients and cloud servers. Secure communication protocols rely heavily on public key mechanisms to unauthorization of the servers. Hash functions further support cloud security by verifying data integrity and detecting unauthorized modification. Together, these cryptographic mechanisms enable secure storage. Major cloud provides encrypt customer data both at rest and in transit. Even if someone gains unauthorized access to physical storage drives, the encrypted data transmission remains unreadable. Common mistakes in cryptographic implementation. Even when storage strong we have been strong algorithms are chosen, improper implementation can introduce server vulnerabilities. One common mistake is using outdated or weak algorithms that no longer meet modern security standards. Another critical error is handling or hard-coding cryptographic keys directly into source code, which exposes them to an attacker through reverse engineering. Poor key management practices such as failing to rotate or securely storage keys significantly increases the risk of compromisation. Using predictable or insecure random number generates can weaken encryption strength, as randomness is essential for generating secured keys and installation vectors. Additionally, improper validation of digital certificates can expose a system to man-in-the-middle attacks. Attempting to the digital custom cryptographic algorithm instead of relying on well-tested and standardized libraries often results in critical flaws. These mistakes demonstrate that cryptographic security depends not only on strong mathematical but also on carefulness of the implemented and of operational disciplines. Quantum computing. Quantum computing represents a major technology advancement that has the potential to disrupt current cryptographic system. Unlike classical computers, which process data in binary bits, quantum computers use quantum bits or qubits that can exist in multiple states simultaneously due to quantum superposition. This capability allows quantum systems to solve certain mathematical problems far more efficiently than classical mechanisms may widely used. Asymmetric cryptographic algorithms rely on mathematical problems that are used difficult for classical computers to solve, such as factoring large integrity. Future of cryptography. The future of cryptography is shaped by rapid digital transformation, increasing cyber threats that involves computational capabilities as data generation grows exponential and digital system becomes more interconnected. Digital systems becomes more cryptographic mechanisms must become more robust, scalable, and adaptive. One of the most critical future developers is post-quantum cryptography, which aims to secure systems against the potential power of quantum computers. Additionally, which aims to secure systems against the potential power of technologies such as blockchain. Internet of Things environment, artificial intelligence systems, and large-scale cloud infrastructures. Automatically in key management, zero trust architectures, and stronger encryption standards will play a major role in shaping secure digital ecosystems. The continued advancement of cryptographic research is essential to maintaining digital trust in an era of constantly evolving threats. Conclusion: Cryptography is a core discipline within cybersecurity that enables secure communication and reliable data potential in modern digital environment. It has evolved from simple substitution method used in ancient times to highly mathematical system securing global Internet infrastructure. The four foundational goals, confidentiality, integrity, authentication, and non-reputation, remains central to every cryptographic application. Symmetric encryption provides efficiency of large-scale data protections, while asymmetric cryptographic enables secure key exchange and digital signature. Hash functions ensure data integrity, and hybrid cryptographic systems combine multiple techniques to balance performance and security. As technology advances and threats become more, cryptographic continues to adapt, ensuring that the digital system remains trustworthy and resilient. Takeaways: Cryptography servers are foundational of modern digital security by protecting information throughout mathematical transformation and secure key management. Its primary objective, confidentiality, integrity, authentication, and non-reputation, form the basic of secure communication system. Symmetric encryption offers high-speed protection of bulk data, while asymmetric encryption supports secure key exchange and digital signatures. These are the our learning website. Our learning website. You can start learning by using this URL. And this is our WhatsApp channel. You can, if you have any clarification or doubts, you can scan this and you can communicate through this.